Hello, my name is Eber Barbero, and today I'd like to talk about how to write code for an Abaqus UMAT and then how to use it from Abaqus CAE. UMAT stands for User Material. It allows us to expand the material library of Abaqus. That means that if there is a material model that we know and we like, and it has not been implemented in Abaqus, we can implement it. Now, with UMAT, like most material models available in Abaqus, the UMAT represents local material behavior. By local, we mean that the material responds to the local state, stress, strain, temperature, plastic strain, whatever, at the Gauss point. Now, the material response is not affected directly by the material state at other points in the body. Indirectly, yes, because other points have an influence on the stress and strain, but not directly. For non-local response, that sometimes is necessary, one can use Abaqus UGENS that integrates the response through the thickness of a shell. And I have another video to illustrate how to program and how to use Abaqus UGENS. Right, so in this video, we're going to discuss two things: programming, how to program UMAT, how to code it, and then how to use it. As far as programming, the most important things are to understand the properties, props, and to understand the state variables, SDV. And as far as using the UMAT, there are three key things. One is how to enter user material properties in Abaqus CAE. Second is how to create a job that links to the UMAT. And third, how to display the results using SDV results. So with that, now we go to the first part, which is the code. Okay, so first we want to learn how to write or code UMAT, and then we will learn how to use this in CAE to solve some problems, do some simulation. So the UMAT, the best way is to start with a template. Here I have a template, subroutine UMAT, and this template I got it from the Abaqus documentation. And so the template starts with the heading of the subroutine, and that lists all the variables that will communicate with Abaqus. And you cannot change any of these variables. You cannot change the dimensions of these variables, which are here, either. This is fixed because I don't have access to Abaqus code, so we cannot change Abaqus code, and Abaqus is going to call it like this, so we are to keep this exactly fixed, all right? Now the meaning of all these variables, you can read the documentation. I will explain some of them. There are two particularly that give you flexibility to do the programming, and these two are props and state V. Props is an array of length n props over here, and it contains numbers, parameters, that you know for the simulation you're trying to do. These are usually material properties, but can be also geometric properties like ply thickness, lamina thickness, whatever. So any number of parameters that your material model requires, you put in props. I will show you in CA how you do that. You enter all those numbers. CA will count how many you put, and then it will say, okay, here's an array with those numbers, and it will make it available to your subroutine UMAT. All right, so the other variable that gives you flexibility is state V. State V is the same as, it's called SDV in CAE, and it's called state V here, all right? I didn't change the name, this is the way Abaqus names it. All right, state V, it's an array of length n state V right here, and this value in CAE, you have to say how much it is, and how much it is how much you need for your model. In our case, we need 4 state variables. And so what Abaqus is going to do is going to allocate an array called state V of length 4 in this case, for our example, for each Gauss point, and every increment or frames are called in CAE. And that is going to be in memory, and Abaqus is not going to do anything with that. You have to set and update those values, and that's where you put anything that has to go from one increment to the next, like plastic strain, and anything that you need to get out as a result, because all the state V, which in CAE are called SDVs, are accessible to for visualization in the output database, and we can visualize by that. All right. So now this template is written in fixed format, and fixed format is Fortran 77, and it is a pain to work with. But I have another video in which I force the compiler, Intel compiler, to interpret extension.for as free format. That way I can write in fixed format, mix it with free format. You have to watch the other video to set up your system in order to use this capability of UMAT. So next, here in this UMAT that I'm making available to you, I comment some variables. This was not in the template, but I added to help you. And you can read all these. And here is props again. And in our case, n props is 11, 5 elastic properties, and 6 strength values. And here is state V. And state V, we're going to have 4. And these 4 state variables correspond to 4 failure indexes. So IF1 to 4 are failure indexes. Failure indexes are inverse of safety factor. And that means that if the value is less than 1, it's okay, and the inverse is the safety factor. And if it is more than 1, it means it failed. And we're going to compute 4 failure index with TMS, fiber tensile failure, fiber compression failure, fiber shear failure, and matrix cutoff. All right, so, okay, if you don't know what I'm talking about, you can read truncated maximum strain, which I call TMS, in section 732 in this book. And this book is my intro book for composite materials. And then later with CAE, we're going to do this example, which is example 313 modified for TMS. So I call it example 313 underscore TMS. And this is in the Abaqus book. Okay. So now we know all this. Next thing I want to say is that you define what is the order of the properties in props. So you see here is props 1 is E1, props 2 is E2. You define this. But once you define, you have to remember and enter the properties in this particular order. And so we have 5 elastic properties and 6 strength values. And then there are some properties that I don't need to put in props because I can calculate, and that is there. And then in the subroutine, I have this calculation for the elastic stiffness, which I don't need for TMS, but I put it there because you may use it if you want to write a UMAT for a stress-based criterion. Then you need the stiffness so that you can calculate the stress. Calculation of the stress is here. Abaqus works on strain. All right, so the driving variable is the strain, and I have to calculate stress from strain. For TMS, I don't need because TMS is a strain criterion, but I just left it there for the future. And so then finally, I got here a call to TMS FC is the name of the subroutine. That's the real subroutine that is going to calculate the failure indexes for truncated maximum strength for TMS. And okay, so I call this, and the reason I make it into a separate subroutine, here's the subroutine, TMS FC. The reason I make it into a separate subroutine is that I want to be able to debug and test this subroutine outside Abaqus. I do it in Visual Studio, and when I know the subroutine is good, then I bring it over here. All right, so again, here I list the SDVs. How come? They were STV and now they're SDVs. Well, the conversion is done here. When I call the subroutine, I call it state V because in this part of the code is called state V, but then when it arrives over here, it becomes SDV. All right, and I did this not to confuse you, but to force you to think about SDV because in CAE, the state variables are called SDVs. And of course, we have 4, 1, 2, 3, 4 for the failure indexes. All right, and then the rest of the code I'm not going to explain because it's just a bunch of formulas. And you can go to section 732 in my book and you read about it and you write those formulas here. And that's it. There is nothing else to do. Okay. So next, what we're going to do is we're going to use CAE to set up a simulation. And we're going to call this code and make this code our material model. And we're going to get results and visualize those results. Okay, so now what we're going to do is we're going to see how we use a UMAT from CAE. And I'm not going to show you how to build a model with all the mouse clicks because it takes a long time, and I have other videos that show that. I did it ahead of time, and what I'm going to do is I'm going to show you what is on the model database, on the CAE file, all right? And you can download this CAE file from the website if you want, or you can do the mouse clicks to reproduce it, which I'm sure you know. The first thing is we have a part, and if we go here on the tree and open up the part, here is part 1, feature, share, planner, section, sketch. Double click on section, sketch, and this is the sketch. So the plate is 4,000 millimeters long and 2,000 millimeters wide, and that's the sketch. So I click here to get rid of this, and that's it, we got the part. So now we go to material, to property, and in property we have materials, and we got two materials. Unidirectional is the material that I will use with one of the models, failure modes that are already in Abaqus. And in that case, what I will do is I will say elastic property of type lamina, and I had to put 6 properties. Really should be 5 because G12 and G13, you see they're the same. This and this is the same value because the lamina is transversely isotropic. So for my UMAT, I only use 5, but Abaqus wants 6, so I gotta enter 6. And then, so these are the elastic properties. And then I gotta enter the strength, which they call a fail stress. And for that, I gotta double click. And when I double click, I get this. Now for TMS, I need tensile stress, compression stress, and transfer direction stress. And I don't need all these, but I put it because, for example, SIGU needs all these parameters, all right? So maximum stress needs some of these parameters. So that's why I put it. All right, so these are the numbers. And in the same order, here the strengths and here the stiffness, I'm going to use that same order for my user material, okay? So then I go here, this is the user material that I'm really going to use. And so I edit. And that one, how do I pick? I say general user material. So to get here, you do general, and then you use user material right here, this one, okay? But I already did it. And there are two things that you have to specify. DEP VAR, dependent variables. This is the number of state variables, which is called differently in CAE to confuse everybody. And so where do I put that? 4. Remember I told you we need 4, so you put 4 here, so the array over there will have a size of 4, okay? And then you gotta put the user material properties. User material properties, we put 11. Remember I told you there are 11. Those are the same 5 elastic properties, and these are all the strength properties, of which I need only the first 3, but I put all just in case, all right? And once I have that, then I say, okay, and that's it. My unidirectional user is what I'm going to use. All right, so now dismiss that. And so next, what do I have? Oh, okay, we have the section. Of course, we have to create this section, so edit. And in the section, put the thickness of the plate, which is 25 millimeters. And that's it. There is nothing else. I have a section. Dismiss. Then I have to assign the sections. So, okay. I edit this to show you. Section 1, I assign it to this part. This is nothing, right? It's so easy. Okay, then with dismiss, we have that. So once we have all these, then we have assembly. You got to do the assembly. The assembly you know how to do. Basically, you assign the part to an instance. And here's the instance. That means that this part is being assigned to an instance, which is called instance. That's it. So we got that. And so then once we did the assembly, then we got to do the steps. This is so the same in all the examples. We got the initial, then we create another step that we need to apply the load. So we dismiss that. And then we go to load. In this case, we have load and boundary conditions. So let's look at the load, edit. And you can see this is put as a pressure. Here it is, the pressure. All right, so the pressure points this way in the negative direction of the z-axis, all right? And this value, 0.03, is the applied pressure over here. And this applied pressure is going to make this plate bends. And we're going to see that in the results, okay? So I got the load. Load is done, dismiss this. Now we go to the boundary conditions. So there are 2 boundary conditions. Edit this. Now you see this red line here and this red line there. Those two lines have been picked. And what do we apply? Apply U3 equal to 0. That means Z direction is 0 because the load is going that way, and this is going to react, and it's going to produce a simple supported boundary condition. Now U2 is being fixed. That means that the Poisson contraction expansion in this direction is restricted, and whether that is good or not, necessary or not, is debatable to discuss on another day, but at least in the analytical models, that's what they use, so I use the same. Okay, then I go there and then go here and edit this. So you see this red line and this red line both have U3 equal to 0, and you want to restrict the Poisson effect in this direction, and that's that. So we have boundary conditions, and once we have boundary conditions, we look at the mesh. Okay, I have pretty good mesh. All right, very fine to get nice results. And then we go to job, and in job we edit the job to show you. Okay, here there is first tab, there is not much I can do. And here in general, you see down here we have user subroutine. We gotta tell it what user subroutine you want to use. Okay, so how you do that? Well, we click here and we look in our user directory, and I have two user subroutine, but no, don't use that because that is, for example, 311. And now we want to do UMAT TMS, which is different code. So we pick this, and it is there correctly. Yes, UMAT TMS.4. Okay, and then we got it, and once we have that, then we say submit, and it's going to run. Okay, and it's going to take some time because it has to compile the Fortran code of the UMAT, it has to link it to Abaqus, and now it ran Abaqus. And once it ran Abaqus, it checked the file, and now it finished. Okay, so completed, that means that we can look at the results. So results, okay, what results we can see? Okay, well, we can see anything that is on a state variable. So SDV1 is here. And so we can see, all right, maximum is at the center in red. And what is SDV1? Well, you got to remember from the code, SDV1 is the index, failure index for fiber tension, all right? Now, are the fibers breaking in with tensile stress? And no, they're not, because this number is less than 1. If this number is less than 1, it's not breaking. The fibers are not breaking, okay? And the inverse of this number is the safety factor. Okay, so now let's see if the fibers are breaking in compression. So we go there and we look, fiber compression was the 2. And then, oh, what happened? This is 0. That means 0, the index is 0. How could the index be 0? Well, it's 0 because what I'm looking at is the bottom of the plate. And at the bottom of the plate, since the bottom of the plate is in tension, there cannot be any compression, so the failure index is 0. But how do I know it's the bottom of the plate? Well, it's the bottom of the plate because here it says fraction minus 1. All right, fraction minus 1 points to the bottom because Z points upward, positive, minus 1 is the bottom of the plate. I would like to see the top of the plate. So how do I see the top of the plate? I go to result, find section points, and you see here where it says top, click on top, apply. Ah, okay, now I see the top of the plate. The top of the plate, it is in compression. That means that I have a number, and now I can say, oh, are the fibers breaking in compression? No, they're not, because this number is less than 1, and if the number is less than 1, that means that it's not failing, and the inverse of that number is a safety factor for that mode of failure. All right, so good, they're not failing. So now I want to go back to the bottom, so I say, okay, I go back to the bottom. And how about shear? Are the fibers failing in shear? Okay, this is SDV3, is a fiber shear index. Is any fiber breaking in shear? No, they're not, because this number, the maximum, is less than 1, and the inverse of that number is a safety factor, so it's not failing. So finally, what can we check? Oh, we can check matrix cutoff. Is the matrix failing? So I go to 4. And when I look at the plot for the matrix, what I can see is here, this number is 1097, so it's barely failing. It's starting to fail. All right, so when I see this number, then I say, oh, the matrix is failing. And pretty much that's it. We got all the results from truncated maximum strength display for us. And this material model is not available in Abaqus, but you can write it, and now Abaqus can do this for you. Okay, thank you.